So now we're going to be moving to LeetCode problem number 2662, which is a medium level problem that is minimum cost of a path with special roads. So let me just go over the problem statement first, and then I'll go over to the examples, and then finally we'll cover the solution. So you are given an array start where start is equal to start of x and start y. So x and y coordinates of the starting point. It represents your initial position in a 2D space. So we have a 2D space. You're also given array target where we need to reach, which is target x and target y. The cost of going from a position x1 y1 to any other position x2 y2 is x2 minus x1 absolute of that plus absolute of y2 minus y1, which is equal to the Manhattan distance. We know that, right? Now there are also some special roads. You are given a 2D array special roads where special roads of I is equal to x1i, y1i, x2i, y2i, and the cost I indicates that ith special road goes in one direction. Okay, so we know that it is only a directed kind of an edge from x1i to y1i, x1i, y1i to x2i, y2i, with the cost equal to cost I. You can use each special road any number of times. That's also given in the problem. Now we need to return the minimum cost required to go from start x, start y to target x, target y. So whenever you hear the problem minimum cost or shortest path, one thing should always strike you that we can use Dijkstra's algorithm here. So that is basically the intuition part, that when you solve a lot of problems, you get the minimum cost. Whenever you see that keyword, you start thinking in the direction towards the Dijkstra's algorithm. So let us see this example. In this example, we can see that we have been given start as 1, 1 and target as 4, 5. So let me just draw this. So we have 1, 1. Wait a second. We have 1, 1, right? 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So from this is the start node, start point, and this is 4, 5 here, right? So target is 4, 5, and we have special roads. So we see that from now let us mark the special roads. So x1 and y1 are 1, 2. So let us say we have 1, 2 here. 1, 2 is this one, and then we have 3, 3, another node here. 3, 3 would be here, right? And since it is a directed edge, we can make this that from this direction to this x1 y1 to x2 y2, we have the cost equal to 2. Similarly, for the next one, we have 3, 4, which is 3 and 4 here, and another one we have 4, 5, which is the same this one, and there's a directed edge towards the x2 y2, which is 4, 5. So this is the directed edge, and the cost is 1. So if you calculate the distance from here to here, this is Manhattan distance, which is 1. Then this is distance 2. Then this is again Manhattan distance is 1, and this is 1. So 1 plus 2 plus 1 plus 1 plus 1. Sorry, this is the value. This equals to 5. So this is the minimum cost. Otherwise, if you had to go from this point to this point, the distance would have been 4 minus 1 and 5 minus 1, 5 minus 1, and their absolutes added. So that comes out to be 3 plus 4, which is 7. So we need to take the minimum of these, and minimum is 5. Using the special roads, we have reached this point, that is 5. Similarly, you can go over to this example and see and check for yourself that it is optimal not to use any special edges and go directly from starting to end position, because in this example there was a directed edge from 5 to 7 to 3 2, not the other way around. So that is one thing that you need to note, that we have to take care of the directed edge as well. Now similarly for this example, you can check for yourself, right? So now you have understood the problem. So now let us start going over the solution. So I posted my solution in the solutions tab, and it is a very beginner friendly, most simple solution using Dijkstra's algorithm. So intuition is that we want to move from a starting point to a target point. Yeah. So normally we can walk between any 2 points using the Manhattan distance, like moving in a grid. But in this problem, we have been assigned some special roads that can transport us faster if we choose to use them, right? And the challenge now comes to the fact that what will be the cheapest way to reach the target using either the normal movement, that is the Manhattan distance between the start point and the target point, or using the special roads if we can minimize that. So minimize the cost. So that is why we use the shortest path problem, which means Dijkstra's algorithm would be used, as I had mentioned. Now the approach is that we need to model the problem like a graph traversal, where every point in the 2D space is to be considered as a node, since we are going to form a graph, right? We are going to make directed weighted graph, because weight is also coming into the picture. That is the cost of traveling from one point to another, which will be the Manhattan distance. So you can move directly from any node to any other using Manhattan distance. Special roads are like shortcut edges which may cost less than walking, right? Now, second is we have to filter out the helpful roads. That is, some special roads might actually be worse than just walking. So we have to filter these out, special roads which do not minimize the cost, and keep only those special roads where the given cost is less than the Manhattan distance between their endpoints. This is a very key takeaway from this problem, that only those special roads will be considered where the cost is less than the Manhattan distance between their endpoints. Finally, we use the Dijkstra's algorithm So we start from start point with cost equal to 0. Try walking to all special roads start points and taking the road. Update the cheapest way to reach each destination node and keep track of the minimum cost using a priority queue. We'll be using a minimum heap because we have to consider the minimum or the shortest path. So at the end, try going directly to target or from the end of a special road to target. And then we pick the cheapest of all these paths. So that is how we have come to this approach. Now, complexity would be O of R log R, where R is the number of useful special roads, because each special road is processed using Dijkstra, and heap operations take log time. And space complexity is OR for the distance map and priority queue that we'll be using. Now, I'll come over to the code. So this is the coding part. So basically, we need to make directed weighted graph from the special roads. From basically all the points in the 2D space, we have to consider them as nodes so that we can apply Dijkstras. So here, coordinates are nodes in the graph, and the edges are the special roads. And Dijkstra will be used to find the shortest of the minimum cost in the directed graph, as I already told you a lot of times. Now I've made a function of Manhattan distance where it takes points x1, y1, coordinates x1, y1, and x2, y2, so 2 points, and returns the absolute of x1 minus x2 plus absolute of y1 minus y2, that is the Manhattan distance. So straightforward, no rocket science here. Now we're moving on to the minimum cost function, which is our main function. So it takes the start vector in which we have the start coordinates, that is start of 0 and start of y, which I've stored in sx and sy, and the target vector, which has the target x and y coordinates, that is target of 0 and target of y, stored in tx and dy, and the special roads, which have been stored in a vector of int type. So we are going to maintain a map which would store the coordinate as well as the distance required to reach the coordinate, so the minimum distance. So map of pair of int comma int type and int is also there for the minimum distance. So this is the format of distance, and we set the distance of the starting point as 0 because we are starting from that node, so the minimum distance would obviously be 0. Now we maintain a vector of filtered roads of int type, in which we'll be storing the filtered list of roads that have cost less than their Manhattan. So here I had mentioned that we have to filter some helpful roads. So we are keeping only those special roads where the given cost is less than Manhattan distance between their endpoints. So this would be the data structure that we'll be using for that, right? Filtered roads. And now we can make the directed edge from x1, y1 to x2, y2 with weight is equal to cost in order to traverse the graph using the Dijkstra's algorithm. So for auto road in special roads, now since it is given in the problem that we have special roads of I is equal to x1 I, y1 I, x2 I, y2 I, and cost of I. So there are 5 major points here. So we take x1 as road of 0, y1 as road of 1, x2 as road of 2, y2 as road of 3, and cost is this road of 4. So we've extracted the coordinates as well as the cost. So now here we check that if the special road's cost is better than the actual distance, that is the Manhattan distance between the two coordinates x1, y1 and x2, y2. So if the cost of the special road is better, then we push it into the filtered roads, because that is our aim, that we need to push those nodes which have cost less than the Manhattan distance. And then we update the distance, that is the vector, the map, with the coordinates of x2, y2, and we push the value of the Manhattan distance that we are considering, right? Now finally we start the Dijkstra's algorithm. So min heap is used to get the minimum distance. So using t as a tuple in int. So this would be storing the in the priority queue. T is basically, this is the alias that I've used, alias name. So distance x and y coordinates it will be storing, and priority queue is basically used for minimum heaps. That is why we have used the greater element here. So priority queue of t comma vector of t and greater of this. So that is pq. Now we push the minimum distance, that is 0 and sxxy, where we are starting from, that is the start node, into the priority queue, and we start our standard Dijkstra's algorithm. That is, while the priority queue is not empty, we extract the current cost x, y from the top of the priority queue, current cost x and y coordinates, and then pop these elements we have popped, and now we check if the current cost is greater than distance of xy. So if we have already visited xy with a better cost, we skip it. So we continue. Now we move via each filtered special road. So the special roads are in the filtered roads, right, that are useful, the special roads which are useful. So we move via each filtered special road. So again the same for auto road in filtered roads. We are going to extract x1, y1, x2, y2, and cost. Now we calculate total cost, which is going to be the move from x comma y coordinate, that is this coordinate that we have pushed in and extracted as well. So move from this to x1, y1 normally, and then take the special road to x2, y2. That is how we are going to build the logic of getting the total cost. That is the current cost we take, that is this cost, along with the cost that is taken for the special road, that is Manhattan distance plus the cost from going to basically moving from x1 xy to x1 y1 normally is the Manhattan distance of xy x1 y1 and the cost, and to take the special road to x2 y2 we add the current cost, right? So if this path improves distance to x2 comma y2, then update and add to pq, because this would be minimum than the one stored in the distance map. So if total cost is less than distance of x to y2, then we set it as the total cost and push it into the priority queue along with the coordinates. Now we have the minimum most distance to reach every endpoint of the special roads, because in this traversal, while the priority queue is not empty, we'll have all the minimum distances stored in this, and the answer would be basically Manhattan distance of Sx Sy to Tx Ty. So we are basically initializing answer as the final answer as Manhattan distance of going from the start node, that is Sx comma Sy, to the target node at Tx comma Ty, and then we'll update the answer. So minimum answer is going to be either the direct Manhattan distance if we are not considering any special roads, but in case there is a useful special road that reduces the cost, we'll choose that as the minimum cost. So we go over distance unordered map for auto p comma d distance. So we check basically int x is equal to p dot first and y is equal to p dot second. So basically in distance, what we were storing was, I'll show you, pair of int comma int. So this is the p and d is the distance. So p basically corresponds to the coordinates. So p dot first would be the x coordinate. Where is it? Yeah, p dot first is x coordinate and p dot second is y coordinate. And the total cost would be the distance, that is d, plus the Manhattan distance required to go from that xy coordinate to the final tx comma dy. And here we update the answer as minimum of answer and total cost. So the answer that we had initially and the total cost that we have calculated, if in case there is a special road that will help us to reduce the cost, then we will be considering that. So it gets the minimum of these and finally returns the answer. And let me submit it to show you whether it's getting accepted or not. And yeah, it has been accepted.